Okay, in this video, we take a look at the physics definition of work. You've certainly heard of the quantity work before, but oftentimes it's used in everyday language. Physics has a very special definition for work, and it's very much related to the concept of energy. So let's go ahead and define it. Conceptually, work is the means by which energy is transferred between objects. So if we believe in the law of conservation of energy, we need a way of being able to transfer energy between objects, and it's done through the concept of work. Positive work on an object tends to increase its energy. Sometimes it goes faster, sometimes we just lift it up. Negative work tends to decrease it. So we think of work as a verb here. It's a transfer of energy between objects. So when you do work on something, I often say you're working on something. That's a transfer of energy. Easiest definition, this would be a mathematical definition, is when force is constant and acts in the direction of motion. We can write that very simply. Sometimes we just have to go back to the very basics. So work is equal to F times D, right? So force times displacement. Now, technically speaking, when we talk about displacement, we sometimes use the term delta X. That's fine. It's just a product of force and displacement. Notice what we're doing is we're combining those things. Like when I go back to the idea of the picture here on the front page, that force multiplied by that displacement could be thought of as the work that that picture does, the transfer of energy that that picture does on that ball by exerting that force through that displacement. So it's simply a product of those things. Now that's, of course, the simplest definition. That's when the force is constant and acts in the direction of motion. Certainly the world is not that simple, but let's start with that as a fundamental idea of work, a force through a distance. The SI unit for force is the Newton. Right? We should know these things. We could write that as a kilogram meter per second squared. Right? So the Newton is a derived unit. These are fundamental units or base units. The SI unit for distance is the meter. That is, of course, a fundamental unit. The SI unit for work, then, is the Newton meter, or sometimes called the joule. Of course, the joule is 1 Newton meter is 1 joule. Named after James Prescott Joule, did a lot of work on this concept, pun intended, quite a while ago. Now, when force acts at an angle to the motion, only the component of force that lies in the direction of motion does any work. So let's go ahead and formalize this equation now. Sometimes the force is not in the same direction as motion, and so when that's the case, you can see the diagram here. The FBD, or at least the force that that person is exerting on that, has some horizontal perpendicular component. We can define that then as work that acts at whatever angle is just F times D times the cosine of the angle between that force and that displacement. Okay, so that theta there is the angle between those two vector quantities. Okay, so a little bit more of a formal definition, a much more applicable to a variety of situations as opposed to this one here. Now, physics requires both a force and a displacement. Oftentimes, a conceptual challenge here is to think that that you are doing work anytime you're exerting force. That's really not the case. There must be both a force and a displacement. Now, I have a variety of pictures here. This person here, a person that's a competitor in the world's strongest man competition, certainly doing work there. This person is pulling along a semi-tractor. There is a force acting, yes, and there is displacement acting. Yes, he's moving that semi-trailer. There's positive work being done here. Now here we have a force, yes, but there is no displacement. Right? So there, even though he's pushing hard against that wall, there is no work. Simply because there's no motion there. Now this is a hoverboard, and sometimes I don't always get my hoverboard out, but once I push this person and get them moving along, they just continue to move along at a constant speed with no force acting. Newton's first law says an object in motion will stay in motion unless acted on by an unbalanced force. So this one has some distance, there's some displacement, yes, but there's no force needed to be able to keep the thing moving, so there's no work here. Again, big idea is that you need both a force and a displacement. Now, even though force and displacement are vectors, they have directions associated with them. Work is a scalar quantity. It has no direction. Thank goodness, because vector quantities are somewhat hard to work with. Work itself is actually scalar. Now, it can be positive, it could be negative, and that, again, depends on the angle between the force and displacement. Now, a person lifting weights here, when they lift it upward, the force is up and the displacement is up, and so the work is positive. But when they lower it, when they lower it, where the displacement is down, notice when they lower it, the force is still up, right? So when they lower it, the work is negative. Of course, the Earth is also exerting force on those dumbbells as they lift up. So when the person is lifting those dumbbells up and exerting a force in the direction of motion, at the exact same time, the Earth is exerting that force downward, opposite direction of motion. So when the person is lifting the dumbbells up, he or she is doing positive work on those objects. The Earth is doing negative work at the same time. The opposite is true when they lower them. Over here, again, we have the same picture that you saw from before. Work in the direction of, or that force in the direction of motion means that there's positive work being done by that rope on that box. So certainly there's friction acting as well. Friction would be doing negative work if the object is moving to the right and friction is acting towards the left. This one's sort of tricky. This person's carrying things around the orchard. It looks like carrying this maybe this bushel of apples. Even though there is a force and there is a displacement, there's no work. And the reason for that is because that force has to be at least somewhat aligned with the displacement. So if I were to go F d cosine theta, what we would see is that the angle of theta is 90 degrees. Simply because the force that he is exerting is up, the force that the Earth is exerting is down, and the motion is perpendicular to that. And so the angle between them is 90 degrees, and there's no work, there's no transfer of energy going on between that person and the bushel of apples. Over here, certainly this would be an example of positive work, provided that person is causing that car to move. Negative work here, because that person is exerting a force in the opposite direction that the ball is moving, right? So that would be an example of negative work. In common projectile, we've studied projectile motion before, there is a force of gravity acting. I'm going to zoom in here a little bit so we can see this better. There are periods and locations along the path of this projectile where the Earth, which is the only object exerting force on this projectile as it moves through the air, where the Earth is doing positive work and where the Earth is doing negative work. So let me use some color coding here to make this easier to understand. The instantaneous direction of the displacement there is along that green arrow, and the direction of the force is down. This is force due to gravity. I'm not drawing an FBD here. Right? This is a instantaneous displacement vector showing which way it's moving at that point. This is a force vector, so it's not an FBD. But clearly you can see that while the projectile is rising, the Earth is doing negative work on the projectile while it's rising, because that force of gravity is acting mostly in the opposite direction of motion. Now, the converse is true over here. When I look on this side, I see that the force of gravity is now more aligned and in the same direction as the way that this object is moving instantaneously at that point. So now the Earth is doing positive work on that projectile. There is one place on the projectile where the Earth is exerting force but not doing any work, and that is, of course, right up here at the very top of the apex. The instantaneous displacement vector would be this way. And while that's occurring, the Earth is pulling straight down with force of gravity. And this you might recognize as a centripetal force, which does not do any work since it's perpendicular to the way that object is moving. So no work up here. And that's, again, work done by the force of gravity. Okay, let's take a look now at just a couple of examples to finish up this video. Two athletes push on a 250 kilogram sled. Tom pushes horizontally with a force of 105 newtons for 12 meters and jumps in. Bob pushes with a force of 115 newtons at an angle of 25 degrees below the horizontal. Interesting. For 14 meters before jumping in, should this be called a bobsled or a Tom sled? A little play on words there. We often call these things a bobsled. Let's call it after the person who does more work. Let's go ahead and determine that here. So anytime I want to determine the work done on an object, I might want to know what that object is that's doing that work. Let's do the work done by Tom. Whether it be the force that Tom exerts times the displacement through which Tom is exerting that force times the cosine of the angle between that force and that displacement. So here's Tom, pushes horizontally, so that means the cosine is the cosine of 0 degrees, which is 1. And he pushes with a force of 105 newtons for 12 meters, so that's no problem. 1,260 Newton meters, or we'll call that 1,260 joules. Okay, and it looks like maybe I've lost my sig figs there, but that's okay. Let's just keep an extra one. Let's call that 12.0, so I don't round too much there. Okay, and let's go ahead and do the one for Bob. So work done by Bob is equal to the force that Bob exerts multiplied by the displacement through which that force is acting times the cosine of the angle between that force and displacement. Being very literal there with that equation. Let's see, that's 25 degrees below the horizontal. You might be tempted to put that in as a negative 25. Doesn't really matter, but I'm going to go back to my unit circle for a second. 25 degrees above, 25 degrees below. You notice they both have the same cosine value, which is the x component, right? So it doesn't really matter whether or not it's negative 25 or positive 25. They both have the same projection along the x-axis, and so we can go ahead and just use the cosine of 25 degrees. Let's go ahead and put in these numbers here. Let's see. So Bob pushes with more force, 115 newtons. A different distance, that's 14 meters. But we have to consider the cosine of that angle. And so when we put in all that stuff to determine his work, I'm getting about 1460 Newton meters, or 1460 joules. So let's go ahead and call it a bobsled, since Bob actually did more work in that problem. Number two, a catcher stomps a 146-gram baseball moving at 95 miles per hour. This goes back to the idea of Newton stopping that ball that Aristotle was through. He applies an average force of 2,600 newtons. It actually is a very large force. And the reason for that is because of that very small distance, that 5 centimeters. And so that force through distance is the work that has to be done. If I only have a little bit of distance to be able to exert that force is going to have to be pretty big to be able to take the energy away from that ball. So how much work does a catcher do? Be careful about considering the direction of force and displacement. So let's go ahead and be very literal with this equation. Work, again, is a force that let's see, how much work does a catcher do on the ball? So I'm going to say the force that the catcher exerts on that ball, force times displacement times the cosine of the angle between the force and the displacement. So let's see, that's 2,600 newtons. The displacement is, I'm going to put this in meters so I can get Newton meters out of that, 0.05 meters. And the cosine, hopefully you caught that, that cosine is of 180 degrees, opposite direction, right? The ball is moving this way, the force that's acting is this way, so that angle is 180 degrees. And so from that, we can calculate that work. And I'm getting negative 130 joules. The negative is important there. That catcher is taking away some of the energy of that ball. And so you can think of that work, again, as a verb, a transfer of energy. We are reducing the energy of that ball by 130 joules. Okay, let's do one last slide. Sometimes we are considering the total work done. When we have multiple forces acting on an object, the network, which becomes a really important quantity throughout all of this unit, the network done on the object by all of these forces can be found by two methods. And so it really is up to you on which method you want to use. You can find the work done by each force separately and then add them with the appropriate sign. You can also determine the net force and then use that to determine the net work. So let me just simplify that right over here for a second. We use the symbol sigma W to represent net work. I could write that as sigma force. That's the net force multiplied by the displacement. Again, those are vector quantities, multiplied by the cosine of the angle between those two, right? So that'd be maybe the simplest way to do it. Other times, we might want to determine the work done by separate forces and add them. So I could just as well write that over here as the total work is work 1 plus work 2 plus work 3 plus dot, 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 work n. Some of these might be positive, some might be negative. I do have to be careful about that. Depends on which way that force is related to the is acting in relation to the direction. Let's go ahead and just take a look at this problem down here. Force of tension 150 newtons, force of friction 95 newtons, the displacement 8 meters, the angle of 25 degrees. Let's go ahead and just try this in both methods. So the work done by the force of tension, the work done by the force of friction. the work done by the force of gravity, the work done by the normal force. These are the four forces that are acting on that object as it's moving through that displacement of 8 meters. Notice that all of these forces, though, have different angles in relation to the way it's moving. So when I go to do this, it's going to be the force of tension multiplied by the displacement, multiplied by the cosine of the angle between those. Well, let's see, 25 degrees. Maybe the cosine of 25. I'm not going to put those numbers in there because I have a limited space, but let's see, the force of tension is 150 multiplied by 8, and then multiplied by the cosine of 25. And with that, I get 1,087.6 joules. Okay, so I'm just going to leave all those there because I'm going to compare that to this one here. The work done by friction, well, that would be the force of friction multiplied by the displacement multiplied by the cosine of the angle between those. Well, that's 180 degrees, right? Because the friction is acting opposite direction as moving. So that'd be 95 multiplied by 8. And that I get negative 760 joules. Okay, it's negative because of that cosine of 180. The work done by gravity, well, I can go through and do that. I have, I can't actually do that because I don't have the weight of that. I don't have the mass of that crate, but that's okay because whatever that force of gravity is multiplied by the displacement, the angle is 90 degrees. And so there is no work done by gravity, thank you very much. And the work done by the normal force, by the same idea. The weight force and the normal force are opposite direction there. So this would also be the cosine of 90 degrees, and that would be 0. So I could add them all up. I'm going to do that. I get 1,087.6, subtract away 760, and I see the total work is just simply 327.6 newtons. Scrap that. Make sure I have those units right. I'm the instructor, I should have those things down. 327.6 joules is the total work. A transfer of energy of that much from 4 different objects exerting forces. Now let's take a look at how we might do this over here. You might find this simpler. Let's first determine the net force. So I have that force of tension, which we said was 150 newtons at 25 degrees. I have the force of friction, which is 95 newtons. I don't know the weight nor the normal force, but I do know that those two things are going to not end up doing any work. So I might just take this as a component this way, minus the force of friction times the displacement, and then times the cosine of 0 degrees, since it's moving unbalanced force towards the right, and the object is moving towards the right. So let's just go ahead and do that. 150 times the cosine of 25 minus 95 multiplied by 8 will give me that as well. So let's just check that. 150 cosine 25, that's 135.94. Take away 95 from that, I get 40.995, and then multiply that by 8. And sure enough, I get 327.6 joules. Found another way. Sometimes it's easier to do this one. Sometimes it's easier to do that. And there we go. That completes the first lesson on work for AP Physics C Unit 3.